I'd like to highlight that part of the work that I show today is also done by two really great bachelor students. They've run some individual models that now all get together to this comprehensive study. And yeah, I'm going to talk about coronae. Let's see if the slides are up. All right, I'm particularly going to talk about asymmetrical coronae. And I'm going to quickly go through this presentation because we're already a little bit behind. Yeah, as I said, this is co-authored by the people mentioned on the slide. So next slide. All right, you can already click next slide. So tactonism, that's basically the topic of this session. I shouldn't highlight it too much, but here I really like these visuals of highlighting the differences of these ideas between mobile lid and squishy lid. And Sue already gave a really great introduction amongst also the other presentations before. So I would like to focus more on this idea of the squishy lid for Venus. Next slide, please. That really involves all these diapairs and mantle plumes and also creates a lot of tectonic features. Next slide, please. So this is just a little bit of an overview, and you can already click next slides because I'm going to focus on these magic coronary features that seem to be very popular today. So next slide. Joe already gave or others as well, gave already a good introduction. I'm here just showing kind of the distribution amongst the surface. These are of at least 350 of these corona features. So you can see that they're really widely spread out. A lot of them occur near rift zones, but definitely not all of them. And as has been mentioned before, there are a lot of different shapes and dimensions and volcanism associated with these structures. So next slide. So I'm going quite fast. Yeah, I just wanted to highlight some models of these plume lithosphere interactions that could potentially cause corona features. On the top, I've had some really, so from the LPI abstract of Joe, so he showed that already earlier, but there are also some older models, analog and numerical. And yeah, as I'm an author of the paper, I'm kind of continuing the work, next slide please, on the models that were published also. Oh, next slide. Yeah, sorry. That were published a few years ago in this paper. And the thing that came out of this paper was like we saw a lot of different kind of tectonic volcanic processes associated with different types of corona structures at the surface. But we only investigated this kind of homogeneous, smooth interaction between a rising mantle plume or diapair and a homogeneous structure above. But when we had to look at coronae in real life, or like the data that we have, corona are not as simple as these models show them in terms of topography, at least. So next slide, please. So yeah, what we wanted to do is the same corona that were analyzed in our previous paper, which are basically the largest corona that are present. We reanalyzed them a little bit in terms of their topographic profile and their like their situation amongst the in the region, like what the topography is in the region around it. So it's going to be a lot of next slides. I'm sorry. So you can go next slide. And then another next. So basically what we identified is whether a corona is radially symmetrical or not. And as you can see, most of the corona are actually radially not symmetrical, so they show different topographic features at different arcs. And so this is all in terms of topography. And then amongst those asymmetrical corona, we kind of identified whether they are intrinsically asymmetrical. Next slide, please. So so that, for example, we saw in this Nightingale corona, like this is a corona plotted in an otherwise kind of homogeneous, smooth topographic area around it, but the corona itself shows a lot of distinct features at different arcs. Next slide. So we found that also a lot of corona are actually situated along a topographic margin, so that part of the corona is bounded by a plateau that is higher in terms of topography. And then also there are a lot of corona, next slide, that are very irregular, occur clusters, and most of these corona are actually situated in these sort of Shasmata rifting like zones, like shown here. That is just very difficult. So next slide, please. So here I show the distribution that we found, and what I just like to highlight, I'm not going to talk about it too much, is that we found that all these localities of these red triangles are actually corona that are actually situated along a topographic margin. And then I'm not showing it here, but if you compare this with kind of crustal thickness maps, it would also really like kind of argue that these topographic margins also represent crustal thickness margins, like a crustal plateau along a crustal lowland. So next slide. So that's what motivated us to do some numerical modeling. I'm not going to talk about this too much, but I just want to show here that we're modeling in 3D a rising mantle plume that impinges upon a crustal, heterogeneous crustal structure, so a lowland next to a plateau. And this is a different crystal structure, but we also in some models model different lithospheric structures, so where the plateau is actually older and colder. So I'm gonna ask to do next a few times to skip time a little bit. So next slide or two, yeah, yes. So these are just some highlights. I'm not gonna talk about them too much, but this is a really good teaser for my LPSC talk, where I do have the time to go into the details and also analyze the results a little bit in the next weeks. But we see various different dynamics happening, so lowland-sided subduction or even plateau-sided subduction and lamination, which is quite interesting because this really depends on this crustal and lithospheric structure of these plateaus. So I'm gonna ask next 3 times, I think. Check. Yeah, one more, and then another one. Yes. So this is just a teaser that we find on the left, the lowland-sided subduction models, and on the right, the plateau-sided subduction and dripping models. That these are all really related to the different setup in our model. So you have different crustal plateau thicknesses, different strength of the crustal plateau, which is in fact controlled by the thermal profile. So we are now analyzing these models further, and I think like this, I'm going to end this talk and invite you to have a look also for LPSC talk. That the question will be hopefully answers why these models are so different and what we can say about Venus because of it. Thanks.
Thank you, Anna.